Welcome to The Explainer. Today, we're mapping an absolutely monumental evolutionary leap in artificial intelligence. We're talking about moving away from passive reasoning engines, systems that merely generate text, and transitioning straight into the era of active, autonomous AI agents. We're going to look really closely at the underlying architecture, the system prompts, and the integration of specialized tools that actually make this leap possible. By the end of our time today, you'll understand the precise technical vocabulary and the exact engineering stack required to turn a static, statistical model into a dynamic, independent operator.
Okay, let's dive into this. We are taking a bottom-up systems engineering approach today, essentially building an agent piece by piece. We're going to cover the limitations of LLMs, the anatomy of an agent, the ReACT framework, the integration of contextual memory, MCP servers and tools, and finally, multi-agent systems.
Section 1. Limitations of LLMs. To really appreciate where we're going, we first have to establish what this core reasoning engine actually is. So, large language models are fundamentally highly complex statistical tools. They utilize deep neural networks trained on incredibly vast text datasets to make probabilistic word-level predictions. Now, because of the sheer scale of their training parameters, they exhibit what we call emergent behavior. They can suddenly perform logical reasoning, solve math problems embedded in text, and chain complex thoughts together. But make no mistake, despite this emergent behavior, they are not truly intelligent or sentient entities. They don't possess a real-time understanding of the world. They're essentially just incredibly powerful pattern-matching engines.
And that brings us to their primary limitation, which is, well, paralysis. Think of an LLM as this brilliant brain, but it's trapped in a jar, without any hands. It has absolutely incredible text generation capabilities. It can perfectly compose a highly nuanced, contextually appropriate email to your client, but it cannot authenticate with an SMTP server. It literally cannot click send. It's entirely isolated from external action. It always requires a human operator to bridge that gap between text generation and real-world execution.
Section 2. Anatomy of an agent. This is where we give the brain its limbs.
So how do we actually solve this paralysis? Well, we enter the second phase of our engineering stack, the agent. An agent is essentially a software wrapper. It encapsulates the large language model and equips it with specific programming functions, APIs, and tools. Through very carefully engineered system prompts, the agent is given overarching directions about its exact role and the specific capabilities it has at its disposal. It completely bridges that gap between the isolated neural network and the external digital environment. So the crucial point here is that we are combining two very distinct layers. The LLM acts as the CPU, the central processing unit driving all the cognitive decision-making and planning. Meanwhile, the action space represents the physical capabilities, the APIs, the search functions, the database queries. When you combine a powerful reasoning engine with a defined action space, you achieve true autonomous execution. The system can now plan a task and actually execute the whole thing without any human intervention.
Section 3. The ReACT framework. Because having limbs isn't enough, the agent needs a logic layer to use them effectively.
And that brings us to the ReACT framework. This is a highly structured architecture for agentic workflows, and it operates in a continuous iterative loop. Step 1 is reason. The LLM generates a reasoning trace, analyzing the user's request and deciding on a specific course of action. Step 2 is act. Based on that thought, the agent selects a tool from its action space and executes a command, like, say, querying a web search API. Step 3 is observe. The agent ingests the result of that action, assesses if the overarching objective has been met, and if it hasn't, it triggers the loop all over again.
This brilliantly illustrates the resilience of the ReACT framework. What happens if the web search fails or the database returns an error? Well, in classical programming, the script just crashes, right? But in agentic workflows, error correction is a feature, not a bug. Because the LLM is probabilistic, it evaluates the error message during the observe phase, utilizes looping notes, and dynamically corrects its own logical path. It actually realizes, oh, okay, that API endpoint failed, I'm going to try this other search tool instead. That self-correction is exactly what makes these agents truly autonomous.
Section 4. Integration of contextual memory. We have a brain, we have hands, and we have a logical loop. Now, we need a nervous system.
Because without memory, an agent basically has complete amnesia after every single prompt. We solve this by implementing two specific types of memory architectures. First, we use thread IDs to manage short-term memory. This groups consecutive API calls into a single session context, allowing the agent to maintain the flow of an immediate conversation.
But for true long-term contextual persistence, we use embeddings databases. This allows the agent to permanently store user preferences, historical interactions, and environmental context across entirely different sessions.
This is a massive game changer for the user experience. By utilizing Retrieval Augmented Generation, or RAG, the agent pulls from its embeddings database before it even begins its reasoning trace. It totally prevents repetitive querying. For example, if you ask it to book a dinner, it already remembers your favorite Japanese restaurant and that you prefer dining at exactly 7:15 p.m., simply because it retained that data from an interaction you had 3 weeks ago. It operates with a highly personalized, persistent contextual awareness.
Section 5. MCP Servers and Tools. Our standalone agent is highly capable, but hard-coding every tool is incredibly inefficient. It's time to scale up.
Enter the Model Context Protocol, or MCP. Instead of building tools directly into the agent's local environment, developers deploy an MCP server. Think of this server as a centralized repository of capabilities. When our AI agent needs to perform a task it doesn't natively know how to do, its MCP client reaches out to the MCP server using asynchronous calls. It basically asks, hey, what tools do you have available, and dynamically borrows the necessary function in real time.
Now, what's really interesting about this toolset is the Python REPL tool. This is an experimental, highly powerful feature. Let's say a user asks the agent to calculate a complex future value on compound interest rates, a task LLMs traditionally fail at because of their probabilistic math limitations. The agent can dynamically borrow the Python REPL tool. It will literally write custom Python code, execute that code in a secure sandbox, and return the exact deterministic mathematical result. It's absolutely wild.
Section 6. Multi-Agent Systems. We are now ready to move to the final, most advanced tier of this architecture. Let's look at how this builds from simple to complex. A single agent architecture handles your standalone tasks, like a basic support bot. But in a multi-agent system, you deploy multiple specialized models with entirely distinct roles. You might have a sales agent, an inventory agent, and a logistics agent all collaborating to solve a problem. And how do they coordinate all this? They communicate dynamically, either by generating natural language that the other agent reads, or by passing highly structured JSON payloads via standard HTTP protocols.
But, of course, this level of interconnectivity introduces significant system risks, which is exactly why compartmentalization is an absolute engineering necessity. You literally have to physically and programmatically separate agent access. For instance, you might have a healthcare web search agent and a separate patient advising agent. If they share the exact same tool space, the web search agent might accidentally ingest private patient records and leak a user's cholesterol levels to an external search engine. So strict boundary controls and isolated MCP server access are absolutely critical to preventing catastrophic data breaches.
We have journeyed from a parallelized statistical text generator all the way to a dynamic, memory-augmented, self-correcting entity that's capable of borrowing code execution tools and collaborating in specialized ecosystems. The architectural leap here is just staggering. So I'm going to leave you with this final thought. As these MCP-backed multi-agent frameworks become the industry standard, how will this fundamentally rewrite our traditional software engineering workflows? The era of writing static scripts is ending. The era of orchestrating autonomous agents has officially begun. Thank you so much for joining me on this explainer.